Good morning. Today we are going to take another important step in our lateral handling, our handling dynamics or lateral dynamics of our course vehicle dynamics. What do you mean by vehicle handling? So vehicle handling is what is called the responsiveness of a vehicle to the driver input. So I give a steering during my motion of my vehicle, maybe a moderate or high speed in highways. I have to take a turn. What is the responsiveness of my vehicle for the given steering input is what is called vehicle handling. Or you can say vehicle handling refers to what is the ease of having a control in your vehicle, the directional control in your vehicle. The vehicle is never go to an unstable state in the yaw plane, in a ground plane. So unstable state refer to what? The spinning of your vehicle in the ground. Instead of having a turning radius of the actual car, the turning radius becomes zero at a critical speed of your vehicle, and that condition is what is called an yaw unstable state. So which is never preferred to get it, and it would happen particularly in a vehicle which is designed for oversteer effect, or the vehicle which is understeer vehicle is changing to oversteered vehicle because of some other operating condition or loading condition, or you are not looked at so far braking during cornering. If you apply braking during cornering, there can be a chance that the understeer vehicle changes to oversteer behavior, and the speed of your vehicle is going to be dictated, limited by a critical speed. At that time, you would see that the curvature of your vehicle become infinity, and you would have a radius of turn becomes zero, and you see that slipping out of your rear axle, and then vehicle would be spinning. So that is what is the unstable state of your vehicle. So that should never be invited in your vehicle, right? So that is what is lateral dynamics is all about: studying of control of vehicle and studying of an unstable state of your vehicle is what is lateral dynamics, or in sense you can call it as vehicle handling. So today what are we going to do is, so far we have looked at in our lateral dynamics aspect the steady state motion of your vehicle. In the last class we looked at three important steady state gains derived from the respective transfer function by applying final value theorem of Laplace transform, right? So any differential equation solution will have two parts of solution. One is transient solution, another one is particular integral steady state solution. So to get your transient solution, you should look at time tends to zero. What would be the response? The transient response would die out at the appreciable smaller time interval. So initial value theorem, when you apply, you would get what is called impulse response function, or that is what is your transient solution. But to get your steady state solution, you have to make your time tends to infinity. So you have to look at your response of a vehicle after giving an input after some time. So as the time is progressing, you see that your vehicle would respond to that input that what you have given to the vehicle, and that motion is what is called a steady state motion. And equivalently, what you do that by applying final value theorem. That is the reason why you have substituted in transfer function s tends to 0 to get this steady state gains. And we looked at those three steady state gains. What are those three steady state gains we have looked at? Is yaw velocity gain, lateral acceleration gain, and curvature gain. And they had given you a physical insight to look at the vehicle tendencies. What we are talking of neutral steer tendency, or understeer tendency, or oversteer tendency. And these steady state gains are quite useful metrics to do a comparison among the class of vehicles under different operating conditions. So with that background, so for what we have studied, we are just going to look at now an important aspect called the role of your vehicle. So when I say role of your vehicle, why we are going to see that is an addition to what we are doing now is, so far in our bicycle model, we have not considered the role of your vehicle. Why is it so? Is because the entire vehicle mass is considered to be as one rigid mass, and your front axles are collapsed as considered a single wheel, and rear axles are collapsed and considered as a single wheel. So this is what we have looked at our vehicle as, and the effect of suspension was not accounted in our lateral dynamic study so far. But we have understood to explain your handling, steady state motion is sufficient, and we derived a fundamental governing equation for that, which was relating to metric called understeer gradient or understeer coefficient. So this understeer gradient or understeer coefficient is dictated by tire compliances. So there is a front axle tire compliance as rear axle tire compliance, right? So this is all something that we have studied. So the tire compliance was given due importance instead of the suspension effect so far in our bicycle model. The moment I have to account my suspension effect, I need to consider my vehicle mass discretized into two masses as an unsprung mass, which is below the suspension axle and wheel mass, is called an unsprung mass, and above suspension, what is that is there is called a sprung mass. So you discretize your vehicle as these two masses, and you'll have an axle mass, unsprung mass role, as well as sprung mass role relative to an unsprung mass. So there is a roll, and the roll will take place about an axis called roll axis, and there is roll moment distribution in front axle and rear axle. These all are going to be now brought in your vehicle model. So this is what we are going to see in our this lecture and the next lecture. Maybe we will take the role of suspension onto the vehicle role in the next period, the derivation. But whatever the basic understanding or the physics required, all is what I am going to explain you in this particular period. And for that, let me share my screen. I hope you are able to see the screen. And this is lecture number 26, and today's date is 13/10/2021. And what is that we are going to do is, see, there are two, I'm just going to give you some idea about handling again as this OEM test conducting is concerned. We have looked at three important tests in our previous lecture. What was those three important tests? Constant radius test, constant steer angle test, or constant speed test. So what is that essentially you are doing is you are trying to look at the vehicle tendencies, and these tests on a real vehicle when you do, what is that you can do is you would be able to look at a real-time understeer gradient effect in your vehicle. Whereas in a bicycle model is an analytical model and an equation that may not be reflecting the real scenario of vehicle from understeer changing into oversteer condition because of these additional design aspects. Particular design aspect is the suspension steering system aspects. So as the sprung mass rolls, there will be a steer effect in your wheels, and that would change your understeer gradient. This is an example. Like that, you have other effects that comes from camber angle change, or your bushes in connecting parts of various subsystems on your vehicle. So there are many other design aspects that would also contribute for change in this understeer coefficient, what you derived considering the steady state motion. So that is what can be looked at from those three tests, what you have seen, and we have also understood what you mean by handling diagram. If you look at, there are tests called open loop test and closed loop test, correct? So what do you mean by closed loop test? Closed loop test. So this closed loop test is what is going to address the handling, which is called overall measure of vehicle driver combination. So Closed loop test, the driver would observe the environment. He'll give a vehicle, he understand the vehicle condition, and he has to take his vehicle in his path. So what he will do, he will give a steering input and correct it, and then every time there will be feedback how vehicle behaves in driving environment, and he would do accordingly the input, and then vehicle get driven in a controlled direction manner, and that is what is called closed loop test. So the driver observes the vehicle direction and position and corrects his or her input to achieve the desired motion is what is you can say closed loop test, or it's not test we are talking on, closed loop system of your vehicle, right? It's called a closed loop system. So closed loop system is vehicle driver combination. Another one is called the open loop system. The open loop system, if you look at what is open loop system, your driver is not going to give any correction measure. Your vehicle would be given some input, and then the vehicle motion would be absorbed, and such thing is what is called an open loop system. What is the purpose of this open loop system and the test in a vehicle is to understand the directional behavior of the vehicle. Is to understand the directional behavior of the vehicle. Directional behavior of the vehicle for the given specific steering input, right? Or you can say precisely it is directional response behavior of your vehicle, correct? One specific input is given. What do you mean by that? You drive your vehicle and you give pulse steer. Pulse steer means what? You steer and then get back. What is the response you measure? That's one. You are not having a controlled motion, like you have to overtake a vehicle, you have to give a steering, and then you have to counter steer so that you can do double lane change test. So that is closed loop. You want to correct your vehicle the way you wanted is closed loop system. Open loop system is something you give an input to the vehicle and observe what is its directional response, and that is what is open loop test. So one such test is you drive your vehicle, give step input, give a steering and hold it. So the steering what you have given accordingly what is happening to your vehicle you observe, that is what is directional behavior of your vehicle observation. Or you give a pulse steer and see what is happening to your vehicle. That is what is the open loop test to understand the directional response of your vehicle. So these are two popular vehicle system and the test environmental condition to put this handling study of your vehicle, handling study of your vehicle. What is this open loop system that we looked at so far is steady state motion. Steady state motion. We have derived a parameter called Understeer coefficient, KUS. And you know what is the fundamental governing equation of steady state motion is Fy is equal to MRU, or M is at equals 0. So these are the equation. And from this, what did you get is a fundamental governing equation that's representing delta F is equal to L by R plus KUS into AY by G. AY by G, right? AY by G. So here this KUS is what is this Understeer coefficient. So this is the governing equation. So far we have looked at your vehicle open loop system. This KUS is what is the metric to describe the directional behavior of your vehicle so far in our study that we have considered. And what is that you have to understand here is you have looked at this L by R is in unitless, so radians. So this is in radians. So your AY is given in terms of this is what the meter per second square. G is 9.81 meter per second square. So there is no unit. So this all can be in radians is what we have seen the unit for this. If that is so, what is the unit you see in other textbook? So I'm going to have this lecture reference is from textbook by Thomas Gillespie, Fundamentals of Vehicle Dynamics. Thomas D. Gillespie. Fundamentals of Vehicle Dynamics. So in that chapter number 6 is what is steady state cornering, and you would refer that maybe for today's lecture and tomorrow and one more lecture for that. So if you look at in that textbook, this equation is given in terms of degrees. So you should not worry about it. If it is to be changed into degrees, you would have this L by R is multiplied by 57.3 times L by R. How does it come? 2 pi is radians is equal to 360 degrees. So 360 by 2 pi is the multiplication factor that comes here. If that is so, this would be in degrees. So what is this? It's called the steering angle. Right? Steering angle of the wheels which are interacting with the ground. So then here this KUS, and you will have here this AY is given in G unit. This AY is given in G units. Right? So this is expressed in G's. That means it is not meter per second squared. Rather, you would say it is 0.2 G, 0.3 G, like that. Right? In terms of G values, it is given. If that is so, how do you define your KUS? The unit of KUS now is going to be degrees per, what is that unit of that? Degrees per G. Degrees per G. So what I mean by that is what is the slip angle? So you see this KES here is what is the slip angle in an axle per G lateral force imposed on that is what is defining this KUS. Because now this KUS, what you have studied, is nothing but difference in WF by C alpha F minus WR by C alpha R. What are these called? These are called individual terms called tire compliance. Tire compliance. So, unit of the load in the front axle is in Newton, and this would be in Newton per, this is stiffness. So, stiffness Newton per degree slip angle developed is what you take. So that you will have this is in degrees, right? Degrees per G. So, how do you have to define a tire compliance as this way? A slip angle at an axle, slip angle at an axle per G lateral force imposed at that point. So you have to define tire compliance as like that. So if it is a front axle, you have this because of this, what is the slip angle at the axle per G lateral force imposed on that would be defining my tire compliance. So here what do you get? Degrees per G. So if I represent like that, your understeer gradient would be represented in this equation like that. Don't